Hi, and thanks for joining us. Today, we'll be having a look at capacitors. We'll have a look at some types of capacitors, see how capacitors are used, understand something more about capacitors than what most people probably know or maybe even want to know. You know, I hear so many people saying capacitors store charge. Well, that's only half correct. Capacitors store energy. Capacitors have two electric plates with an insulator in between those plates. And each one of those plates carries a particular charge. But because the charges are opposite, the charges cancel out, so the net charge is zero. However, there is energy in joules stored in an electric field inside that capacitor. And when we start to charge a capacitor, electrons travel to one plate, causing a surplus of electrons on that plate. The surplus of electrons causes electrons to be repelled and migrate across to the opposite plate. When they get to the opposite plate, we end up with an excess of electrons there, and hence electrons have to leave that plate and go back to the charging voltage source, leaving what we call electron holes on the opposite plate. So therefore, one plate becomes negatively charged, one plate, because it has an excess of electrons, one plate is positively charged with a deficit of electrons. It has holes, what we call electron holes, and we have the dielectric in between. And we have this is an induction process, of course, that causes the electrons to migrate, and we have the insulating dielectric in between, and therefore we have this electric field which is set up between the two plates inside the capacitor. And if we explore this, if you look in your books, you're going to find an equation which is the energy in joules as half the capacitance times the voltage squared. Well, the fact is that energy in joules is equal to the charge times the voltage. But the charge equals C times V. So if we go charge or capacitance, but if we go capacitance times voltage, we'll get capacitance times voltage squared. But as this little capacitor is charging, and we've got that induction process happening with electrons being repelled from one plate to the opposite plate, we've got a voltage developing across those plates which is equal to and in opposition to the charging voltage for the capacitor. So therefore, the more charge that we get on each individual plate, the more that capacitor is bucking the process, let's say, of taking any more charge into each plate. So the charging process slows down the more the voltage rises across the plates. Anyway, enough about that. Let's have a look at some capacitors. This is one huge, big, oil-filled capacitor. And I might even zoom in on this later. It actually says PCB free. It hasn't got any of those nasty chemicals in it. Could have been found in capacitors some years before. This capacitor, very interesting. I wouldn't be putting my fingers across the top if it did not have these bleed resistors. It has some 120k resistors across each terminal on the capacitor. And that is because if we leave this capacitor in a charged state with several joules of energy stored in this capacitor, and somebody was to come and put their hand across that, they could get quite a fatal electric shock across it, purely because of the high voltage characteristics and high capacitance value of this particular type of capacitor. So you should always have bleed resistors across big capacitors. Other capacitors that we use in electronics, this is a large non-polarized capacitor called a green cap. I think that might be a proprietary name, not 100% sure. Polyester capacitor. And that looks to be 0.68 microfarads. We have some small electrolytic capacitors. We have two electrolytic capacitors here, quite low value. One is 100 microfarads and one is 47 microfarads. All right, from here, we'll go across and we'll have a look then at the charging characteristics of the capacitor. We'll put a current meter in series and we'll put a voltmeter across the capacitor with some problems that you're going to see, because voltmeters have that dreaded internal resistance, and it's not the best way to do this experiment. So we'll take a few looks at how we can monitor the charging voltage and charging current characteristics in our capacitor. All right, let's have a bit of a look at how this thing charges and, for that matter, discharges. So we've got a 20 volt battery, we've got a power supply. That's good enough, 20 volt battery. We have a microammeter. We have a voltmeter going to 20 volts. The microammeter is currently set to 500 microamps, full scale deflection. That's that middle range there. And I have a 56 k ohm resistor in series with I suppose that's pretty important. Let's find out what we've got here. We've got a 100 microfarad. Let's write that down. 100 microfarad electrolytic capacitor. There's positive there. So when I close this switch, the capacitor will charge. It'll get electrons, in fact, flow from the ground up to put a surplus of electrons onto this plate here. And then with induction, we have the excess electrons migrating across to the opposite plate, and the opposite plate then loses electrons to leave electron holes here. So this plate becomes more positively charged with respect to this plate. In fact, they both carry exactly the same charge. As I said before, the charges cancel to just leave stored energy in the capacitor in the form of an electric field. So let's have a look at this. Let's apply some current to the circuit by closing this switch. Therefore, the charging process should take place. We should get quite a rapid, quite a high rather, amount of current at the beginning of the charge. Then the current should drop back to zero, and the voltage, which starts at zero across the capacitor, well, that potential difference is going to increase to equal the 20 volts from the battery. Is it all going to happen well for us? Let's find out. Let's connect that up, and we saw the current meter spring up here to about 350 microamps, but then, oh dear, look what's happening. It seems to have stopped, and we've only got 5 volts across the capacitor. So what's going on? Have we done everything correctly? I'm pretty sure we have. We have a voltmeter across the capacitor, series resistor, microammeter, 20 volt supply. Look, it's stopped. Nothing's happening. All right, why is that so? Let me explain why. All right, I've got an ohm meter here, and what I'll do, I'll take the current away from our circuit. The meters drop back. The capacitor discharged very quickly. Look, it's gone from 5 volts down to 0 remarkably quickly. I'm going to take that lead off there so that I've just got the 20 volts on the meter. I've got this manual ranging meter connected to the 20k range, and I'm going to put that across our voltmeter. And our voltmeter measures 20,000 ohms of internal resistance. I mean, all voltmeters have to have high internal resistance. This one has 20,000 ohms. Let's look at the maths on that. If we've got 20,000 ohms, if we've got 20,000 ohms in the voltmeter, it acts like a resistor like that, and then we had 56k above it, 56k, and up here we had plus 20 volts. Here's ground. Well, that's a voltage divider. We're measuring the voltage at that point there. So what's happening? Well, voltage divider, Vs times R2 over R1 plus R2 equals V out. So we've got 20k divided by 70k. Let's just move this up. 20 divided by 70 times 20 volts equals, guess what? It's around about a quarter. So a quarter of 20 volts is around about, say, 5 volts. So that's why we only got 5 volts on the meter. You can't use a standard meter like this in an experiment where you've got a resistor of 56k charging the capacitor. It's just not going to work out. So we have to get a better meter to put across the capacitor. So what I'm going to do, I'm going to disconnect that meter. He's going to go for a holiday over there. And then I'm going to get a better meter. All right, so I've got a better meter now. This meter has 10 million ohms of internal resistance. 10 million ohms. So let's put him over here where we can see him. We can see him clearly there. Good. Got him over there where we can see him. And we'll do this experiment again. Now I have the 10 million ohm resistor across the capacitor. So no more 20k. We've got now 10 meg ohms. Dramatic increase. This should work pretty well. All right, let's try again. Supply the charging current. It jumped up to about 350 microamps. The voltage started down at 0 across the capacitor, and it's still charging. Look, it's on its way to 20 volts. This time it should get all the way to 20 volts. Well, we've got 19.8 volts showing on the supply, so it should reach 19.8 volts, providing that meter on the supply is correct. Charging current, not quite down at 0 yet. In fact, the charging current on that meter will probably never go all the way down to 0. Can anybody think why? Well, this has still got 10 million ohms of resistance, and we have got 56k ohms above it, so we still do have a voltage divider, and we're going to have bleed current going down. This is, after all, a 500 microamp meter, so we're probably always going to have around about a microamp or something of current flowing down through that 10 million and 56,000 ohms of resistance. But that worked out pretty well, 19.8 volts, and it came down over a certain amount of time. I'm going to disconnect my current, and I'll get a piece of wire and short circuit that. So we'll do that again. Small capacitors like this, it's okay to short circuit. Large capacitors with a lot of joules of energy, I would not be doing that. Quite dangerous. So look at this, the capacitor is self-recharging. It's already started to go back up, 17, 18, it's got 190 millivolts just sitting on the plates now. So capacitors can charge themselves just from electrons in the air. All right, let's put some current on that. Very quickly up to 5 volts, 8 volts, 9 volts, 11 volts. I can hardly keep up. 13 volts, 14, 15. Current coming down rapidly. Now things are slowing right down. We had a massive dramatic surge in the voltage across the plates in the first second or so, and now towards the end things slow right down. And that's what we said. We've got this voltage, equal voltage across the plates of the capacitor opposing the source voltage from the supply, and that's what gives us our V squared on 2. We have to use the average voltage in our equations to work out the energy in the capacitor because of the slow charge towards the end with that opposing voltage. You can see here the capacitor is discharging. It's discharging via the 10 million ohms from the meter, because I have the meter connected across the capacitor plates, 10 million ohms of digital meter. That capacitor is slowly discharging into that 10 million ohms. We've already lost almost a volt. We're down to 18.9. We'll be down to 18.8 shortly. And if you just leave that circuit there, work out what the time constant for this circuit is. That'll be R times C, and then multiply that by 5. That should tell us how long it's going to take to discharge that capacitor. And I'm willing to bet that the time constant for that is pretty long, with 10 million ohms of resistance and 100 microfarads of capacitance. In this next segment, I have a wonderful little box which I made up to demonstrate capacitor charge and discharge time, and using a comparator to switch a couple of LED colours. This comparator is an operational amplifier. We probably haven't studied this in the part of the course that you're currently doing. However, this has a very, very high input resistance at this point here and this point here. So where we saw in the last segment that we do not want under any circumstances a resistance across this, which is going to load the circuit down and form a voltage divider between here and ground. This is ideal because that large resistance, probably more than 1 million ohms, won't affect our circuit too much. So I've got R and I've got C here, and we've learned that the first time constant, 63.2% of the supply voltage. So after one time constant, this point here has charged up exponentially, very quickly. I've shown that almost as a vertical line, to 63.2% of the rail voltage. So this is a reference point set up with a voltage divider between R1 and R2. That reference voltage is set, and if I set that at 64%, say, of 12 volts, well, when I turn the circuit on, this capacitor starts at 0, and then it quickly comes up towards that 64% of 12 volts. And when it does, and when it gets just a fraction, like 0.0001 of a volt higher in voltage than this point here, the output of this little critter, which was sitting at 12 volts, now swings rapidly and goes down to 0 volts. So by selecting the appropriate voltage divider set point, or by changing the value of R, or by changing the value of C, we can change the timing characteristics of this circuit and cause the output to switch from high to low or low to high. Very, very versatile circuit in the world of electronics and used in so many pieces of equipment. In this little box of tricks, I already have the circuit that we just studied built up. So what's going to happen when I push the button in, we're going to actually discharge the capacitor, which is currently charged up, and hence no current is flowing into the capacitor. We're going to discharge the capacitor, and then we're going to watch the capacitor current decay, and we're going to watch on the oscilloscope the capacitor voltage rise exponentially. So I hold the button down, and we have maximum current flowing, 500 microamps. On the oscilloscope, we've got the trace disappeared down to 0. And when I take my fingers off the big button, don't panic, we see the current rapidly decay, and one time constant, it's going to drop 63.2%. The voltage in one time constant rose 63.2%, and the set point there just changed, and the LED switched over when I got to the threshold voltage set between the voltage divider and the new voltage from charging the capacitor on the negative terminal of the operational amplifier. I've changed this potentiometer, and now I've reduced the threshold voltage on the voltage divider in my circuit, so that when the capacitor starts charging, it does not have to charge so much now before the operational amplifier, called a comparator, changes state. Watch. Here we go. Charging current dropping. Oh, there we are, 2, 4. It looked like 4, 5 volts. That's on 2 volts per division. Let's do it again. You can see there, drop down to 0. It's about to charge, charging to 5.8, about 5.8 volts. The state changed because of the threshold I had set. Charging current, still dropping, slowing right down because the voltage on the plates on the capacitor is fighting with the supply voltage. And there we are, we've flat topped here. We've reached the full 12 volts of the supply going into the capacitor. I'll just change that to a slightly different setting one more time. Discharge the capacitor, let it go. We had 5.8 last time, 2, 4, 6, about 6.5 volts that time. Maybe one more time for good luck. Start again, you can see the oscilloscope drop down. 4, 6, 8, 8.2 volts, about 8.2 volts that time. All because I changed the reference voltage between R1 and R2, that is the set point on the comparator. I have here some capacitors in the back of this old oscilloscope. It's an old cathode ray tube oscilloscope, pretty well obsolete these days. These capacitors are possibly dried out. They are ELNA brand, E-L-N-A, made in Japan, and although they date back to 1980, the funny thing is they're probably still, they'd be touch and go. They might still be okay. I have seen that particular brand last a long time. But these capacitors are used in the power supply. We have some smaller capacitors here, a group of 4, and we have 1, 2, 3, 4 quite large value capacitors here. These were very common to see in older equipment that did not have switching power supplies. This has a linear power supply, and it has these large value capacitors, which sadly do dry out over time, as I said. So, as you can see, I absolutely love capacitors. I love capacitors because they can be used in timing circuits, and there's virtually not one piece of electronic or electrical equipment which does not utilize the qualities of a capacitor. And soon we'll learn about inductors and its resistance, inductance and capacitance, that as passive elements in electronics and electrical circuits, you can make so many devices and gadgets. So this has been Greg Moore for New South Wales TAFE. I hope that you found that interesting, and I hope that you keep watching the next part in this series of electronics. Okay, bye for now. Okay, take 3. So we see this equation, half CV squared, and let's examine where that equation comes from. Where does the half come from and where does the squared come from? Well, energy equals charge times voltage. So charge, if we look at charge, charge is capacitance times voltage. So we actually have energy equals capacitance times voltage. That's where we get the voltage squared. So that gives us our capacitance times voltage squared. But what about the half? Well, as the two plates are charging and we've got the holes developing in the positive plate and the electrons developing in the other plate and the negative plate, and then that resultant voltage, the potential difference between those two plates, is bucking the charging voltage for the capacitor. And because the charging voltage is being opposed, then we've got this slowing down of the charging process as we get more potential difference across the plates. So the further we get into the charging process, the slower the charging process is. So when we charge a capacitor, we start off with a very fast charge, up to, as we'll see, 63%, and then after that, things slow down, and it almost comes to a grinding halt at one point. And we almost come to a grinding halt. So it's the effect of the potential difference across the plates opposing the charging voltage, which is causing us to have to use an average value of voltage in our equation. And the average, of course, is just simply V on 2. So that's where we get C times V squared on 2, which, if we look at it another way, mathematically, it's just half C times V squared. So it's not rocket science, it's a simple little equation to work out the energy stored in the capacitor measured in joules.